Hey everyone, welcome back to Mechanics of Materials. And in this video, we're going to be talking about allowable stress and the basic design relationship. And we'll be taking our first foray, giving you an introduction into engineering design. And as you know, engineers design lots of things. Engineers, civil engineers, and mechanical and bioengineers design buildings, beam components, column components, piping components, piping systems, shafts, stents, uh, gosh, prosthetics, a lot of things, right? And really, the idea behind design is to, in engineering design, is to select material and geometry, okay, like cross-sectional area, steel, aluminum, composite material, select the material and geometry to satisfy performance requirements, cost, and nowadays even things like sustainability, right? And when I say performance, we're talking about safety. Is it safe enough? Is the material not going to fail? Material failure. We're going to prevent that so that we prevent collapse of the whole system. And then cost, is it optimal? Optimizing the material use, right? Is it constructible or buildable manufacturing wise? Is it easy to manufacture? So manufacturing, construction, cost, those are all related. But here we're going to, as it relates to mechanics of materials, our design is focused on having a material and selecting a proper amount of geometry so that we stay within stress limits. And really, when we talk about materials, we want to know what is the limit of that material. Okay, and really that is where material testing and and having knowledge of your material and what your margin of safety or safety factor comes into play. So for instance, let's just say I'm like, oh, whoa, let's say I'm an elevator designer right here, right? I'm an elevator designer. Bam, I design elevators. And I design this elevator and I have some cables that go all over the place like this. And I test my elevator designs. And what I notice is that my elevator fails when I load it. Like, so the cables here fail. So I'll put F fail. They fail at around a load of about 4,000 pounds. Okay, so when I test what I designed with the material that I've used, maybe some steel cable and all these connections right here, I notice it fails at about 4,000 pounds. And so when I specify a margin of safety, I want to ensure that I never reach this level of 4,000 pounds. And so what I'm going to say is, hey, here's what I allow you, the user, to have. Okay, I'm going to say that the occupancy limit of this elevator has to be less than or equal to, or let's say what we can allow is equal to, let's keep it equal to, what is the failure load that I've measured and tested, based on the material that I've chosen, divided by a factor of safety, okay, some margin of safety. And so I might say that, oh, for all elevators, the occupancy limit must be a factor of safety of 2, okay, of 2. So I'm going to say that you can't put more than 2,000 pounds, or people cannot come into an elevator and weigh a total of more than 2,000 pounds. Otherwise, the elevator is going to fail. Now, failure can be defined as snapping of the cables, yielding of the cables, a mechanical malfunction, who knows, right? All kinds of things. But here in mechanics of materials, we're going to relate that to some sort of material failure. So when we relate it to material failure, this F fail relation, this relationship right here between what and a failure condition and then an allowable condition that the engineer you specify right here is, this failure condition is like a material property, okay, that we're going to have in mechanics and materials. For instance, this failure, we might define failure as yielding of steel or aluminum, and we'll say that F fail is the yield strength, sigma y, the yield strength of a material, and then the margin of safety is some standard, that, or some limit, that we're going to have that we're going to say that we can accept. And usually this factor of safety is established by some sort of guideline, uh, by industry guidelines, things like the AISC building specifications for steel construction, ASME boiler and pressure vessel code, experience. And some of these safety factors are established based on probability and studying the probability of failure and limiting the probability of failure. And so for now, let's say that in terms of a material that we have, so for a given material, let's say like steel or just in general, one of the limits or one of the ways that we can fail is by the normal stress. And so we have a, the allowable normal stress. So if we want to put this back into stress, allowable stress, the allowable normal stress is going to be equal to the failure stress, and whatever I define as failure. It could be yield stress, it could be rupture, it could be the normal, some sort of normal stress measurement. So some property of the material. Again, I can't emphasize this enough. It's a material property, and then divided by some factor of safety. And sigma allow is essentially what we the engineers say, hey, just use it up to this limit, even though that we know there's some margin for error or some margin of safety. And normal stress is just one way. By normal stress is one way that a material can fail. Something can also fail in shear, and so we would have an allowable shear stress as well. And then we'd have some either shear yield, shear rupture, for a bolt or something, and then as a margin of safety or a factor of safety to minimize or to control what we can allow, right? And obviously the factor of safety, because we're making sigma allowed less than sigma failure, okay, the failure load or whatever it is, this is going to be typically greater than 1. Okay, that's what you'll normally see. This factor of safety is greater than 1. All right, so here we've given you a feel for the allowable stress. In the next video, that's part 2 of this, we'll put this into the basic design relationship and talk about how to get areas out of this. And select, geometric areas, actually specify how much material we need to satisfy a condition. Okay.